Our universe is built on energy. It powers the stars and drives the evolution of galaxies. At the heart of this energy lie nuclear reactions, processes that occur within the nucleus of an atom. These reactions are fundamental to our understanding of the cosmos. Atoms are the building blocks of matter. They are incredibly small, yet they contain immense amounts of energy. This energy is stored within the atom's nucleus, where protons and neutrons reside. Nuclear reactions involve changes in the nucleus, leading to the release or absorption of energy. Imagine the nucleus as a tiny, dense core at the center of an atom. This core is filled with potential energy, much like a coiled spring. When we talk about nuclear reactions, we are talking about ways to tap into this energy. Understanding nuclear reactions is essential for comprehending the universe's workings, from the birth of stars to the development of life itself. Nuclear reactions involve the rearrangement of protons and neutrons within atomic nuclei. These rearrangements can occur spontaneously, as in radioactive decay, or they can be induced artificially, as in nuclear reactors. One type of nuclear reaction is radioactive decay. In this process, unstable nuclei emit particles or energy to become more stable. Imagine a nucleus with too much energy, like a spinning top about to topple over. It releases this excess energy by emitting particles, transforming into a more stable form. Another type of nuclear reaction is nuclear fission. This process involves splitting a heavy nucleus into two or more lighter nuclei. Picture a fragile ball of clay representing a heavy nucleus. When struck with enough force by a neutron, the clay ball splits into smaller pieces, releasing energy in the process. Nuclear fusion, on the other hand, involves combining two light nuclei to form a heavier nucleus. This process releases even more energy than fission. Imagine two small magnets drawn together. When they finally merge, they release a burst of energy, representing the power of fusion. Nuclear reactions are fundamental processes that govern the behavior of matter at its most basic level. Nuclear fission and fusion are two distinct types of nuclear reactions that release tremendous amounts of energy. Although both involve atomic nuclei, their mechanisms and energy outputs differ significantly. Nuclear fission, as mentioned earlier, is the process of splitting a heavy nucleus into lighter nuclei. This reaction is commonly used in nuclear power plants to generate electricity. Imagine a single domino falling and triggering a chain reaction, knocking down a whole row of dominoes. In fission, a neutron strikes a heavy nucleus, causing it to split and release more neutrons. These neutrons then go on to strike other nuclei, creating a self-sustaining chain reaction. Nuclear fusion, on the other hand, involves merging light nuclei to form a heavier nucleus. This process occurs naturally in stars, providing the energy that powers our sun. Picture two soap bubbles colliding and merging into a single, larger bubble. In fusion, two light nuclei, like hydrogen isotopes, overcome their electrostatic repulsion and fuse together, releasing a tremendous amount of energy. The key difference lies in the starting materials and the end products. Fission starts with heavy, unstable nuclei, while fusion requires light, abundant nuclei. The energy released in nuclear reactions is orders of magnitude greater than that of chemical reactions. This vast energy difference stems from the fundamental forces at play. Chemical reactions involve the breaking and forming of chemical bonds between atoms. These bonds are relatively weak and the energy changes associated with them are correspondingly small. Think of a campfire, where burning wood releases heat and light. This energy comes from breaking and forming chemical bonds between atoms in the wood and oxygen in the air. Nuclear reactions, on the other hand, involve changes within the nucleus itself, governed by the strong nuclear force. This force is much stronger than the electromagnetic force that governs chemical reactions. As a result, nuclear reactions release far greater amounts of energy. The energy released in nuclear reactions can be calculated using the famous equation E equals mc squared, where E is energy, m is mass, and c is the speed of light. This equation shows that even a tiny amount of mass can be converted into an enormous amount of energy. This immense energy potential is what makes nuclear reactions so powerful and potentially dangerous. Section 5. Nuclear medicine, healing with isotopes. Beyond energy production, nuclear reactions have revolutionized various fields, including medicine, where radioactive isotopes play a crucial role in diagnosis and treatment. Radioactive isotopes are atoms with unstable nuclei that emit radiation as they decay. This radiation can be harnessed for medical imaging and therapy. Imagine a doctor injecting a tiny amount of a radioactive tracer into a patient's bloodstream. This tracer emits gamma rays, a type of high-energy radiation that can be detected by a special camera. By tracking the tracer's movement, doctors can create images of organs and tissues, helping to diagnose various conditions. One prominent example is iodine-131, used to diagnose and treat thyroid disorders. This isotope emits beta particles that can destroy cancerous cells in the thyroid gland. Other isotopes are used for imaging purposes, allowing doctors to visualize blood flow, bone metabolism, and tumor growth. Nuclear medicine provides powerful tools for diagnosing and treating diseases, offering hope and healing to countless patients. Section 6. Industrial applications, from gauges to non-destructive testing. Nuclear reactions also find diverse applications in various industries, from manufacturing and construction to archaeology and art authentication. One widespread use is in industrial gauges. These devices utilize the penetrating power of radiation to measure the thickness of materials like paper, plastic, or metal sheets. Imagine a factory producing aluminum foil. A radioactive source emits beta particles that pass through the foil. A detector on the other side measures the amount of radiation that passes through. By analyzing the radiation intensity, the gauge can precisely determine the foil's thickness, ensuring consistent quality control. Another important application is non-destructive testing, or NDT, which uses radiation to inspect the integrity of structures and components without causing damage. Imagine engineers inspecting a bridge for cracks or weaknesses. They use a technique called radiography, where X-rays or gamma rays are directed at the bridge. The radiation passes through the bridge and creates an image on a film or detector. By analyzing the image, engineers can identify any hidden flaws or structural defects. Nuclear techniques provide invaluable tools for various industries, enhancing safety, efficiency, and quality control. Section 7. Nuclear weapons, a double-edged sword. The immense power of nuclear reactions, while offering tremendous potential for good, also carries the grave danger of nuclear weapons. These weapons, capable of unimaginable destruction, represent a stark reminder of the dual nature of scientific progress. Nuclear weapons derive their destructive power from uncontrolled nuclear fission or fusion reactions. The detonation of a nuclear weapon releases an immense amount of energy in the form of heat, light, and radiation, causing widespread devastation over a large area. The development and use of nuclear weapons have had a profound impact on global politics and security. The horrors of Hiroshima and Nagasaki serve as a stark reminder of the devastating consequences of nuclear war. The threat of nuclear annihilation hangs over humanity, demanding responsible stewardship of this powerful technology. International treaties and organizations work tirelessly to prevent the proliferation of nuclear weapons and promote disarmament. The future of humanity depends on our collective wisdom and restraint in managing this powerful force. Section 8. The future of nuclear fusion power and beyond. Despite the inherent risks, nuclear technology holds immense promise for a sustainable future. Fusion power, in particular, offers the tantalizing possibility of clean, safe, and nearly limitless energy. Fusion power plants would mimic the processes occurring within stars, harnessing the energy released when light nuclei fuse to form heavier ones. Unlike fission, fusion reactions produce no long-lived radioactive waste and have a much lower risk of meltdown. Imagine a future where power plants generate clean energy through the fusion of hydrogen isotopes, readily available in seawater. This breakthrough would revolutionize energy production, providing a sustainable solution to the world's growing energy demands. While significant challenges remain in achieving practical fusion power, ongoing research and technological advancements bring us closer to this goal. The future of nuclear technology holds immense potential for addressing global challenges such as climate change and energy security. Section 9. Conclusion: Our nuclear future. Nuclear reactions are fundamental processes that shape our universe and influence our lives in profound ways. From the energy that powers stars to the medical isotopes that diagnose and treat diseases, nuclear reactions have revolutionized our understanding of the cosmos and our ability to manipulate matter. As we delve deeper into the mysteries of the atom, we unlock new possibilities and face new challenges. The responsible stewardship of nuclear technology is paramount, ensuring that its immense power is harnessed for the betterment of humanity. The future holds both promise and peril. By embracing scientific inquiry, fostering international cooperation, and prioritizing ethical considerations, we can navigate the complexities of the nuclear age and shape a brighter future for generations to come. Welcome to For Science Salah Lotfy channel. Today we dive into the fundamental building blocks of the universe, elementary particles and nuclear models. How do protons, neutrons, and electrons form atoms? What are quarks, leptons, and bosons? And how do nuclear models help us understand the structure of the nucleus? Before we begin, we extend our sincere gratitude to Professor Dr. Tariq Farooq Nagla, research scientist at the Nuclear Power Plants Authority, Cairo, Egypt, for his invaluable scientific support in providing the material for this course. At the most fundamental level, all matter is made up of elementary particles. These are divided into three main categories. First, we have fermions, the building blocks of matter. Quarks combine to form protons and neutrons. Leptons include electrons and neutrinos, which do not experience the strong nuclear force. Then we have bosons, the force carriers. Photons carry the electromagnetic force. Gluons mediate the strong nuclear force that holds quarks together. W and Z bosons, responsible for the weak nuclear force which governs radioactive decay. Lastly, we have composite particles made up of quarks. Protons consist of 2 up quarks and 1 down quark. Neutrons consist of 1 up quark and 2 down quarks. All interactions between elementary particles are governed by 4 fundamental forces. The strong nuclear force binds quarks together to form protons and neutrons and holds the nucleus intact. The electromagnetic force governs charged particles like protons and electrons, controlling chemical interactions. The weak nuclear force, responsible for radioactive decay, such as neutron transformation into a proton. And finally, gravity, the weakest force but dominant on a large scale, governing planets, stars, and galaxies. To understand how protons and neutrons behave inside the nucleus, scientists have developed nuclear models. The liquid drop model treats the nucleus like a droplet of liquid, explaining nuclear fission but lacking details on nuclear energy levels. The nuclear shell model, similar to electron shells where protons and neutrons occupy energy levels. This explains why certain nuclei are more stable with magic numbers of protons or neutrons. And lastly, the collective model combines both previous models to describe nuclear vibrations and rotations. Protons and neutrons are not fundamental particles. They are made of quarks held together by the strong nuclear force. A proton consists of 2 up quarks, each with a positive 2/3 charge, and 1 down quark, which has a negative 1/3 charge. A neutron, on the other hand, consists of 1 up quark and 2 down quarks. The force that binds these quarks together is mediated by gluons, which act as the glue holding protons and neutrons intact. This model is explained by quantum chromodynamics, or QCD, which describes how quarks and gluons interact at a fundamental level. Understanding elementary particles and nuclear models has major applications in science and technology. For instance, in nuclear energy, improved models help design safer and more efficient reactors. In medical applications, proton therapy is used for cancer treatment, and PET scans are essential for diagnostics. Quantum computing leverages the behavior of subatomic particles for faster, more powerful computations. And in the realm of advanced materials, research on elementary particles helps develop stronger, more durable materials. The future of particle physics is full of exciting possibilities. Scientists are exploring new particles with projects like the Large Hadron Collider continuing the search for unknown fundamental particles. Understanding dark matter is another frontier. Most of the universe is made of this mysterious substance, which physicists are trying to identify. And then there's fusion power, where applying nuclear models could help us harness fusion energy, the key to clean, limitless power. From the smallest elementary particles to the forces shaping our universe, particle physics helps us understand the very fabric of reality. A special thanks again to Professor Dr. Tariq Farooq Nagla for his scientific support in making this course possible. If you enjoyed this video, don't forget to like, share, and subscribe to For Science Salah Lotfy channel. Stay tuned for our next episode where we explore the cutting-edge discoveries in nuclear physics and beyond. Welcome to For Science Salah Lotfy channel. Today we explore nuclear instrumentation and measurement, the technology that allows us to detect, measure, and analyze radiation in science, industry, medicine, and security. How do radiation detectors work? How do we measure radiation exposure? And what are the real-world applications of nuclear measurement technology? Before we begin, we extend our sincere gratitude to Professor Dr. Tariq Farouk Nagla, research scientist at the Nuclear Power Plants Authority, Cairo, Egypt, for his invaluable scientific support in providing the material for this course. Nuclear instrumentation refers to the devices and methods used to detect and measure radiation. These instruments play a crucial role in radiation safety, monitoring radiation levels in nuclear facilities, medical applications, imaging and cancer treatment, industrial processes, quality control and material testing, environmental monitoring, detecting radioactive contamination. Accurate radiation measurement is essential for ensuring safety, compliance, and scientific research. There are several types of radiation detectors, each designed for specific applications. 1. Geiger-Müller counters detects alpha, beta, and gamma radiation. Uses a gas-filled tube that produces an electrical signal when ionized by radiation. Commonly used in radiation safety monitoring. 2. Scintillation counters uses fluorescent materials that emit light flashes when exposed to radiation. Converts light into an electrical signal using photomultiplier tubes, PMTs. Highly sensitive, used in medical imaging and scientific research. 3. Semiconductor detectors made from silicon, Si, or germanium, Ge, to detect radiation with high accuracy, used in nuclear physics research, space missions, and homeland security. 4. Ionization chambers contains ionizable gas that generates an electrical current when exposed to radiation, used for measuring radiation doses in hospitals and nuclear power plants. Radiation exposure is measured in specific units based on the energy absorbed and its biological impact. Sievert, SV, measures the biological effects of radiation exposure. Gray, GY, measures the amount of radiation absorbed by a material. RAD, an older unit of absorbed radiation dose. To ensure worker safety, personal dosimeters are used to monitor exposure. Film badges contain photographic film that darkens when exposed to radiation. Thermoluminescent dosimeters, TLDs, absorb radiation and later emit light when heated. Electronic dosimeters provide real-time digital readings of radiation levels. Nuclear instrumentation plays a critical role in many industries. Let's dive into some of its key applications. First, in the medical field, radiological imaging, using technetium-99m and PT scans for medical diagnostics. Radiation therapy, treating cancer with cobalt-60 radiation. Organ function studies, using radioactive tracers to monitor kidney and thyroid activity. Next, in industrial applications, material testing, where X-ray and gamma-ray scans are used for detecting flaws in metals and structures. Sterilization of medical equipment, utilizing radiation to kill bacteria and viruses. Thickness measurement, monitoring metal and plastic thickness in production lines. In environmental applications, radiation monitoring, tracking radioactive contamination in air, water, and soil. Pollution tracing, using radioisotopes to study environmental pollutants. And finally, in security and defense applications, detecting smuggled nuclear materials using gamma-ray and neutron scanners at airports. Nuclear threat detection, monitoring unauthorized radiation sources in security zones. For precise measurements, radiation detectors must be calibrated regularly. This involves using standard radiation sources like cesium-137 and cobalt-60, comparing detector readings with known values and adjusting instrument settings to maintain high accuracy. Factors affecting measurement accuracy include the type and sensitivity of the detector, radiation energy levels, and environmental conditions like temperature and humidity. Nuclear instrumentation is vital for healthcare, industry, environmental safety, and national security. Without it, we couldn't safely harness nuclear energy, advance medical technology, or protect against radiation hazards. A special thanks again to Professor Dr. Tariq Farouk Nagla for his scientific support in making this course possible. If you enjoyed this video, don't forget to like, share, and subscribe to For Science Salah Lotfy channel. Stay tuned for our next episode, where we explore advanced nuclear technologies and their future impact. We live in a radioactive world. It's a fact of life, as natural as sunshine and rain. But unlike those familiar elements, radiation remains invisible, a silent force with the power to both harm and heal. From the depths of our planet to the vast expanse of space, radioactive materials constantly emit energy, a phenomenon we call nuclear radiation. Understanding this invisible force is crucial in our modern world. It's the foundation for life-saving medical treatments, allowing us to pinpoint and target diseases with remarkable precision. Yet we must also acknowledge the potential dangers. Uncontrolled exposure, as history has tragically shown, can have devastating and long-lasting consequences. This essay aims to demystify nuclear radiation, exploring its various forms, its effects on our bodies, and the crucial safety measures that protect us. By illuminating this often misunderstood topic, we can navigate our radioactive world with knowledge and awareness, harnessing its benefits while mitigating its risks. At its core, nuclear radiation is all about energy. It's the release of energy in the form of waves or particles from the nucleus of an atom. This happens when the nucleus, the atom's tiny but mighty core, is unstable and tries to become more stable. Think of it like a coiled spring holding potential energy that's suddenly released. This release, this burst of energy, is what we call radiation. It comes from various sources, both natural and man-made. Naturally occurring radioactive materials are found everywhere, from the ground we walk on to the air we breathe. They're in our food, our water, even our own bodies. Man-made sources, while often perceived as more threatening, are also prevalent. Medical procedures, particularly X-rays and cancer treatments, utilize radiation for diagnosis and therapy. Nuclear power plants, though controversial, generate electricity through nuclear fission, a process that releases radiation. Not all radiation is created equal. Nuclear radiation comes in different forms, each with unique properties and levels of penetration. Three primary types, alpha, beta, and gamma radiation, stand out as the most common and significant. Alpha radiation, the heavyweight of the group, consists of 2 protons and 2 neutrons, essentially a helium nucleus. While relatively large and slow-moving, alpha particles pack a punch when it comes to energy. However, their size limits their penetration power. A sheet of paper or even our skin can effectively block them. Beta radiation, lighter and faster than alpha particles, consists of high-energy electrons. They can penetrate further, passing through paper but stopped by denser materials like aluminum. Beta particles are commonly used in medical treatments targeting specific cells while minimizing damage to surrounding tissues. Gamma radiation, the most energetic and penetrating of the three, is pure energy, similar to X-rays. These high-frequency waves require substantial shielding, such as lead or concrete, to block their path. Gamma rays are used in various applications, from sterilizing medical equipment to imaging internal structures. Section 4. Measuring the unseen, quantifying radiation exposure. Radiation, invisible and odorless, presents a unique challenge. How do we measure something we can't see or smell? Fortunately, scientists have developed sophisticated tools and units of measurement to quantify radiation exposure accurately. One common unit is the becquerel, which measures the activity of a radioactive source. 1 becquerel represents 1 radioactive decay per second. Another unit, the gray, quantifies the amount of radiation energy absorbed by a material, including our bodies. However, not all radiation is created equal in its biological effects. The sievert, the unit of equivalent dose, takes into account the type of radiation and its potential to cause harm. For instance, alpha radiation, despite its high energy, is less penetrating and therefore assigned a higher weighting factor in sievert calculations. Dosimeters, portable devices worn by individuals working with radiation, provide real-time measurements of exposure. These handy gadgets offer crucial information, allowing workers to monitor their accumulated dose and take necessary precautions. Section 5. Our bodies and radiation biological impacts and safety measures. Our bodies, intricately designed and remarkably resilient, are constantly bombarded by low levels of natural background radiation. We've evolved to cope with this constant exposure, repairing minor damage and maintaining a delicate balance. However, high doses of radiation can disrupt this balance, causing both acute and chronic health effects. Acute effects, typically associated with short-term high-level exposure, can manifest as skin burns, nausea, and in severe cases, radiation sickness. Chronic effects, often the result of prolonged low-level exposure, may take years or even decades to appear, potentially leading to an increased risk of cancer. Understanding the biological impacts of radiation is paramount, as is adhering to strict safety measures. The principles of time, distance, and shielding form the cornerstone of radiation protection. Minimizing exposure time, maximizing distance from the source, and utilizing appropriate shielding materials are crucial steps in mitigating risks. Welcome back to For Science Salah Lotfy channel. Today we explore the incredible world of nuclear energy and its impact on our lives. From electricity generation to cutting-edge medical technology, nuclear energy plays a crucial role. Nuclear technology has revolutionized medicine, allowing us to diagnose and treat diseases with remarkable precision. It empowers industries, ensuring quality control and boosting efficiency. It even helps us explore the cosmos, powering spacecraft on their long voyages. Before we dive in, I want to express my deepest gratitude to Professor Dr. Tariq Farouk Nagla, research scientist at the Nuclear Power Plants Authority in Cairo, Egypt. His invaluable scientific support and expertise have been instrumental in bringing this course to life. Thank you, Professor Nagla. Let's get started. Let's begin with the most well-known application of nuclear energy electricity generation. Imagine the immense power hidden within the nucleus of an atom, waiting to be unleashed. Nuclear power plants harness this power through nuclear fission. Inside a nuclear reactor, atoms of uranium-235 or plutonium-239 are bombarded with neutrons. This causes the atoms to split, releasing an incredible amount of heat energy. This intense heat is used to heat water, transforming it into steam. The steam drives powerful turbines connected to generators, producing electricity that powers our homes, industries, and cities. Now let's talk about the different types of nuclear reactors. We have pressurized water reactors, where water acts as both a coolant and a neutron moderator. Then there are boiling water reactors, where water boils inside the reactor, directly producing steam. And finally, Generation 4 reactors, advanced designs that prioritize safety, efficiency, and sustainability. Nuclear energy offers numerous advantages, including being a clean energy source and incredibly efficient. However, challenges remain, such as radioactive waste and high construction costs, but innovative solutions are being developed. Our journey takes us now to the remarkable world of nuclear medicine. Here, nuclear technology is saving lives every day. Imagine being able to see inside the human body, to pinpoint the location of a tumor, or witness the intricate workings of our organs. Nuclear medicine makes this possible through advanced imaging techniques like PET scans and SPECT scans. PET scans utilize a special radioactive tracer, often technetium-99m, which is injected into the body. This tracer emits positrons, producing gamma rays that are detected by a scanner, creating detailed images of organs and tissues. SPECT imaging works on a similar principle, using radioisotopes to monitor blood flow and assess organ function. These techniques provide invaluable insights, enabling early diagnosis and personalized treatment plans. Radiation therapy utilizes high-energy radiation beams to target and destroy cancer cells, offering hope to millions. Nuclear medicine is a testament to the power of science and innovation, offering powerful tools to diagnose, treat, and conquer diseases. Let's shift our focus to the world of industry, where nuclear energy ensures quality, safety, and efficiency across various sectors. From inspecting bridges to sterilizing medical equipment, nuclear technology is an unsung hero. X-ray and gamma-ray scans reveal hidden cracks, weaknesses, or defects in metal structures like bridges, pipelines, and aircraft components. Neutron activation analysis determines the elemental composition of materials with incredible accuracy. Sterilization uses gamma radiation to kill bacteria and viruses, ensuring the safety of medical equipment, pharmaceuticals, and food products. In manufacturing, radioisotopes play a vital role in thickness measurement and process control. By measuring the amount of radiation passing through a material, manufacturers can precisely control the thickness of products, ensuring consistency and quality. Nuclear energy in industry is all about precision, safety, and efficiency. It's about utilizing the unique properties of radiation to improve processes and enhance our lives. Our journey now takes us to the fields and farms where nuclear technology is playing a vital role in feeding the world. Imagine developing new crop varieties that are resistant to diseases and produce higher yields. Radiation-induced mutation breeding makes this possible, leading to improved crop varieties. Food irradiation helps preserve food and reduce spoilage, addressing the global challenge of food waste. By exposing food products to controlled doses of gamma rays, harmful bacteria, insects, and fungi are eliminated, extending shelf life. Pest control benefits from the sterile insect technique, releasing sterilized male insects to suppress pest populations. Nuclear technology in agriculture and food preservation is about sustainability and ensuring food security. It's about utilizing the power of the atom to nourish our growing population and protect our environment. Our journey takes us now beyond our planet, to space, where nuclear energy powers our exploration of the cosmos. Imagine spacecraft venturing billions of miles from the sun, their instruments still humming with life. This is made possible by radioisotope thermoelectric generators, which provide a reliable power source for spacecraft. Back on Earth, nuclear technology unravels the mysteries of the past through carbon-14 dating. By measuring the amount of carbon-14 in ancient artifacts, scientists can determine their age with remarkable accuracy. Research reactors produce radioisotopes used in medicine, industry, and scientific research. Nuclear energy in space exploration and scientific research represents our unquenchable thirst for knowledge. It's about utilizing the power of the atom to explore the cosmos and pave the way for a brighter future. As we reach the end of our journey, let's turn our gaze towards the future of nuclear energy. Imagine a world powered by nuclear fusion, where atoms are fused together instead of being split apart. Fusion reactions release even greater amounts of energy than fission, with no long-lived radioactive waste. Projects like ITER are working tirelessly to make this dream a reality. Small modular reactors offer enhanced safety features and reduced capital costs, making nuclear energy more accessible. Advanced waste management techniques, including recycling spent nuclear fuel, are being developed to minimize environmental impact. The future of nuclear energy is a testament to human ingenuity and our commitment to sustainability. It's about harnessing the power of the atom responsibly, ensuring a brighter future for generations to come. As we conclude our exploration of nuclear energy, one thing is clear: this remarkable technology is shaping our world in profound ways. It's a testament to human ingenuity, our ability to harness the power of the atom for the betterment of humanity. Once again, I want to express my deepest gratitude to Professor Dr. Tariq Farooq Nagla for his invaluable scientific contributions to this course. Your expertise and insights have been truly enlightening. If you enjoyed this journey into the world of nuclear energy, don't forget to give this video a thumbs up, share it with your friends, and subscribe to For Science Salah Lotfy channel. Stay curious, my friends, and stay tuned for our next episode, where we'll delve into the latest advancements in nuclear science.